Okay. All right, so let's see, get this going. All right, so when we are running a Node.js application, I believe I mentioned this before, is that Node.js runs as a single-threaded application. Can someone explain to me why that would probably be a problem?
It'd probably get pretty slow, right?
Yeah, so if you start hitting it with a lot of different requests from different clients, Node is set up in a way so that it's very like event driven. So like when we were looking at the code earlier, like we have all these callbacks. So that's so that we're not like waiting on like blocks and things like that in the code. So Node is fairly good at like handling different things asynchronously. However, if you have 1,000 or 10,000 like people hitting a single threaded application, you're going to start running into performance problems. So, what might be a way that we can solve that problem? And yeah, I'm going to try to run this like class, so anyone that wants to jump in to try to answer these.
Multi-threaded?
Right, so we could try to multi-thread these applications, or we can try to spin up basically a bunch of different instances of it and a bunch of different processes, which is effectively the same thing. There are some caveats there. So generally this is called horizontal scaling, also called like clustering in some cases. So instead of just having like one Node.js app running to handle all of our things, we could have like a bunch of different instances running. And so, we could run if we're on like a machine that has 16 cores, we could run, 16 side by side or some number. We can even run these instances across different machines. Like we can run them, if we have, 10 different servers, all with like 16 cores, we can run 16 instances on each of those 10 servers. And we can try to use that to like parallelize everything and make it easier to handle the incoming requests. However, we don't necessarily just get that for free. So what kind of difficulties or things what we might have to handle in these cases where we're trying to use a bunch of different parallel instances?
Would it take up a bunch of memory?
It could take up a bunch of memory, but I guess what I'm asking or what I'm thinking about there are a couple of different problems that we have to be able to fix technically in terms of like how the information is flowing around in this case. So okay. So one of the problems is we have to figure out how we're actually going to be handling all of the different HTTP requests that we're getting or all the different connections that we're getting. How are we going to choose where those connections are going? How, what like technical mechanisms are making those choices and are handling that routing basically. And the other problem that we can run into is how do we actually like sync the data between the different instances? Particularly in Node, this often happens in separate processes. So we're not just using shared memory. So we have to use some other mechanisms. But first thing we're going to talk about is sending requests. So some of you have probably heard of this before, but there's a technique called load balancing. which uses an entity called a load balancer um, in your architecture that basically handles the routing of different HTTP requests to the different instances of your applications, or that might be running on different computers, or even within the same computer. That could kind of be abstracted away. So in this case, the load balancer, I think, let's see. So does anyone want to take a guess at like how this might actually function on like a network level? Oh, doing this question and answering is like the sound just very deafening on my end now. I don't even get to see y'all looking at me. But
Externally,
go ahead, BJ.
externally we are will use one common VIP. Whenever we send any request to server, it passes to the VIP, and VIP will meet load balancer, and based on the split at load balancer, it will the requesters will be shared among these app instances.
Right. So I guess I'm trying to get at like what is the, well, we can just talk about it. So what ends up happening is you'll have what will usually happen is you'll have your load balancer will be like the first machine on the network that is actually hit by a request, right? And so it'll be sitting on a public IP address or an IP address that is visible to the clients that are trying to access it. And you can have that on port 80 or whatever, and then it will actually serve as what's called a proxy, or I guess in this case what's called a reverse proxy to these applications. And so it'll actually take those connections and it will forward them by opening up a connection to a different, like an actual Node.js application that might be sitting privately on some other network or just hosting locally on the machine that the load balancer is on, or it could be on some other machine in the cloud in the network somewhere. And so in this case, we have this example where we have like this IP address here, and this could be something as simple as like, or this could actually be the IP address associated with like google.com or something like that. And then, so all of your requests come into this load balancer. It then uses, it makes some decision about where to send those connections to basically a bunch of different parallel applications, which in our case are Node.js apps, but these could actually be any type of technology that's basically running, that's listening for connections. It could be Apache servers or other things like that. So a question that comes up when you're doing this kind of load balancing is, how do you make decisions about where to send connections? And there are a couple of different algorithms that you could potentially consider for doing this. Does anyone have any guesses about what kind of algorithms could be used for making these decisions? So if you've taken an architecture course, you've probably encountered some of these types of algorithms before.
Scheduling algorithms?
Yeah, so different scheduling algorithms. So what are some examples of scheduling algorithms that could be useful here?
Round robin?
Right, so that's one. So can you just explain what round robin is?
So whenever any request comes, like bunch of requests, it will first it will take the app instance one, and then the next this request will be goes to the app next app instance, and Likewise, it will distribute all the app instances.
Right, so it'll just sort of keep rotating around through the different instances.
And again, it will come back the first.
Right. So what might be what might be a disadvantage of using that algorithm in this case?
So it actually distribute equal number of requests to each of one without giving bunch of requests to single app instance.
So that is one potential advantage, depending on sort of how long the connections end up taking for the individual instances. So you might have some requests that take a long time that end up piling up on one server versus another instance that, a bunch of requests that don't take very long. And so you start building up on you could potentially get some imbalance there. Another algorithm that that gets used is just called a simple least connections algorithm, which the load balancer keeps track of how many connections are attached to each instance. And in that case, it would just send new connections to an app instance that basically has the least amount of things hitting it. And so there's another one here called IP hash, which basically what that does is it takes the incoming IP address and source port for the connection, and it runs it through a hash function, and then uses that to assign it to a particular node instance, or to a particular instance that it's load balancing. So can someone take a guess as to why this might be why this would result in behavior that would be something desirable for us? I'm gonna preclude VJ from answering again because he's overachieving.
Could you repeat the question?
So why would implementing an IP hash algorithm where we're hashing the incoming IP address and port for a connection for, I guess maybe not the port, it might just be the IP address, where we run that through a hash function and then use that hash function, probably mod the number of instances that we're load balancing, and then using that to make a decision about where to send incoming connections. What behavior would that give us, and why would that be a good thing?
It would give us security, wouldn't it? Or a little bit more just the IPs aren't direct.
But the IPs aren't going to be direct exactly. Valentine, were you trying to respond?
Yeah, so I think just in case a given server is unable to handle the request, it could always return it back to whatever server passed it onto that server. I don't know if that makes sense.
So I think what a lot of these load balancers will do is they'll have code that checks to see if if a server doesn't respond to a request, like if it crashes or something, it'll make a smart decision about giving that request to another server or sending back some sort of error message. But this particular algorithm doesn't necessarily do that for us. So
I know in general, hashing things makes operations go faster. Does that have anything to do with it?
So it is very fast. Okay, so just as a comparison, if we think about the connection, if we have one client that is making a connection to a load balancer that is balancing across a bunch of different instances, if we do it with round robin, so we're continuously, every like request we make, say we're making a request like 10 times a second, we're making a lot of different connections from a client through the round robin. So what is happening in that case? Where are those connections going? I'll just ask Vincent since she was talking before. Okay, so with round robin, basically all these connections are going to different instances, right? So the IP balancer or the load balancer by design is basically banning all of those connections across all of the different instances. However, if we're using an IP hash algorithm where for each of those connections, where we take a look at the IP address that it's coming from, we hash it, and then we use that to map onto the different instances. So how is that behavior going to be different than if we're just like basically rotating around all of the different instances?
With IP hashing, doesn't it when it goes to the connection, it always goes back to the same server? Is that what it is?
Yes, exactly. It always goes back to the same server. And so why could that be a good thing for us, Jeff?
So that you don't have to keep sending the information between all the servers of what the client had the last session that it had with. Is that what it is?
Yeah, that's actually pretty much correct. So if you're always going back to the same server, that server might have like the session for that particular client cached. So you don't have to like go and reload that out from like your database, or we'll talk about different things different tools you can use for that. But so yeah, if you're using IP hash and your connections are always going back to the same server, you can that gives you some more guarantees about the type of data that might be required by that client. We can maintain our cache for its data. We don't necessarily have to go get it every time, depending on how we implement that. So in some cases, that can be like a really good thing for us, right? But if we're still get a bunch of different connections from a bunch of different clients, and we have a good hashing function, we'll probably still get a pretty even distribution of connections going across to different instances, right? So, so cool. And there are other algorithms too. There's like weighted round robin and weighted least connections, where you can put like weights on the different instances that you're load balancing across. So like if you have one instance that is on a machine that can perform a lot faster than another, then you can weight it in a way such that it'll get more connections and things like that. But we don't really need to go into those details. So one way that you can actually implement a load balancer is by using, there are a lot of different tools out there. I'm going to give some examples of some configurations for a engine called NGINX. So NGINX is this like high performance web engine that's open source. It's written in C, C++, in a very like performance oriented way. And whereas a lot of like things like Node, things like that, JavaScript is a like interpreted or semi-interpreted, like compiled just-in-time language, then it's maybe not as high performance. But NGINX can basically serve as an HTTP server. It can serve up static files. It can act as a reverse proxy, so it can load balancer, and so it can do this type of functionality where we're sending different connections to different instances. Right, and NGINX has a bunch of other functionalities. If you're getting into it, I think it can serve as like a SMTP server for like email. I know it can do like RTMP for like streaming video. It has a bunch of other things built in. But we're going to talk about how it can serve as a load balancer. So this is an example configuration file for NGINX. So I'm not going to go into the details of how you would like set this up. If you're interested in it, you can go and look that up. But in this case, basically what we define what's called like an upstream, which is a collection of different instances of an application that are running and some program that we're interested in. So in this case, we have 3 different servers all on our local host, and they're running on different ports. So on 301, 302, 303. So if we wanted to load balance across those, basically what we do is we set up our server down here. It listens on port 80. Oh, come back. And we specify a particular path that we want to load balance. And then we specify this proxy path, which basically says anytime this load balancer gets a connection at this path, pass it to one of these, proxy it, or pass it to one of these other server connections. And so the default for NGINX is just to use round robin. And so it'll just cycle through all of these. We can change what algorithm we're using for doing that load balancing. So we can do least connections, do IP hash. And this is just an example of like an application that you can use to actually implement this if you're wanting to. And again, this is kind of a production type environment. If you're trying to support thousands of clients or something like that, that you would need to set up. So additionally, traditionally, like these proxies are very good at like passing just like standard HTTP requests, which are again just like I send a request and I get a response and then the connection closes. We can also do that with WebSockets, where the proxy is actually like keeps the WebSocket connection open and opens like a proxy WebSocket connection to an instance and keeps it open, and it's like passing messages back and forth. This is just an example configuration for what that looks like in NGINX. There's some voodoo going on here, which I'm probably not going to explain all of, but you can see here in the server configuration. It's basically having to do some checks and some specific configurations on like the HTTP header options that are getting set, what version of HTTP proxying we're using, and that kind of thing. This up here is like some specific voodoo around basically what I think it's particularly there to handle like opening and closing connections, and it's used to like set these headers in the correct way. But you could use this as sort of like a boilerplate setup for a WebSocket load balancer in NGINX if you wanted to. So that's probably more detailed than you need. But if you want to find out more, I provide a link down here to an article talking about how you can configure it. And there's a lot of, let's see, and there's some documentation I provide here. Something else that you can do with NGINX, which is actually pretty powerful, is you can use it to serve all of your static files. And so, something that we talked about with Node is, I talked about like express.static, which you can use to serve like a directory, which is really good sort of for our toy instances. However, in the case of, a large file server that is hosting a lot of content to a lot of different simultaneous users, Node is probably not the most like performative platform that you would want to use for just serving raw files that aren't changing. Something like NGINX can handle that with a lot better performance, can handle like caching those files a lot better. And so an example like this, we can basically control, if we just want to serve like static files from particular paths, we can do that. But if we have like HTTP paths that handle like different like web APIs where we're making HTTP requests that are dynamically determined by an application like Node, we can say basically pass all instances or all requests along that path to this application that is handling basically these dynamic requests. And so we can split out sort of the performative parts and the logic through using a load balancer / web engine like this. So again, this is like a thing that you would want to use in a production environment, not necessarily just for our toy cases that we're looking at in this class. Again, you can find more at the docs for NGINX. There are other pieces of software that do this. This is just a popular one that I wanted to go over. Are there any questions sort of broadly speaking about load balancing or NGINX or anything like that?
Hi, Professor.
Sure.
Actually, I have a doubt regarding the load balancer. Is it a separate, what are the configurations and all? Is it separate application, load balancer itself, or we can have load balancer along with the application itself?
So in this case, it would be a separate process. It could be running on like the same computer, but generally it would be a separate application. There are probably ways that you could implement it in Node itself, although the implementation is probably more convoluted than would be worth like digging into. This doing it this way, where we sort of like separate it out through like proxy connections and through like having basically different applications with ports open and making like TCP connections between them, like that keeps like basically separates out the it keeps everything sort of self-contained and isolated that way, so that if I wanted to say if I wanted to scale this up, and I wanted to add like 1,000 different instances of Node, and I only had like 10 running now, it's like I could fire all those up on like a different set of machines, and then I could just like reconfigure my load balancer to like also start including those machines. Whereas like if it was within like Node, I'd probably have to like do a bunch of different like special configurations to like probably like restart it, which might have like downtime for like the application and things like that. Whereas like restarting your load balancer can be a pretty fast operation usually. So yeah, the answer to your question is it can be in the same application and you could implement it that way. But my understanding is that typically in a production environment, that's not going to be the environment that you're going to run into.
Okay. Yeah. Thank you, Professor.
Yeah. Okay. Going back to sort of these problems that we have with this horizontal scaling, we run into this issue of like, how do we sync data between like all of these different node processes or all of these different applications that are potentially running either in separate processes or completely on different computers. In order to do this, we want our applications to be what are known as stateless. So we don't want to store data about like the state of particular clients or things like that within the memory of a particular process that's serving these requests. We want that data to be just stored in a way that we can access from any particular instance that is basically that is hosting this service, right? Also, how do we handle like inter-process communication? How do we like send data back and forth, or send messages back and forth between the different instances that are running our application? There are different tools to do this, but one that is typically used with Node is this application called Redis, which is a lightweight in-memory data structure store. It's like a separate application, but it's basically a very lightweight database that is very fast and has been basically programmed to be a very high performance like entity for basically exchanging data, storing data that needs to be quickly accessed, as well as for sending messages back and forth between applications like this. So basically it operates as a hash map. It's just like this big key store where we put in like a value, key value pairs, and that can be any kind of data that we want. Applications connect to it via some kind of network connection, probably a TCP connection where they're just sending these like commands back and forth to like store and retrieve data, as well as messages. So the way that this ends up being structured in architecture is you'll have your load balancer, which is distributing all of your HTTP connections across all of your web server instances, which in this case are Node applications. And all of those Node applications would connect to this Redis application or database. And so you could also do this potentially through something like Mongo, but Mongo is a little bit slower as for optimized for like more complicated data sets, where Redis is more like a quickly accessible data engine. And so, so all of these are connected through to one particular Redis instance, although there are ways to basically distribute Redis across a bunch of different machines and things like that, which we won't really get into, but it basically stores as like a way for caching like data that we need to use quickly. So things like the data storage object or environment for like the sessions for our connections. So we can store all of that data in Redis. So anytime a client connects to one of our instances, we can look up its session inside of Redis. It can then return that to us quickly. And then we can, the client can then potentially make some change to that and then send it back to Redis. So it's like a way for us to keep just basically lightweight data. Again, it's in memory, so if it gets reset or goes down, that it doesn't save that data. So it's not like something like Mongo where it's a persistent data store. It's just something for like to quickly cache data that is being used by a bunch of different parallel applications. If you'll recall, this is how we implemented sessions with Express, where we created a file store. So basically it stored all of the data for a session inside of just a flat file that we had. And anytime some client connected to that, to our Express application, it would look up that session in that file and then use that data to help them make a decision about what content to serve. So in this case, we were like keeping track of the number of views that a client had, number of times they had accessed the page, but you could have more complicated data in here. So again, in this example, this was just stored in a file. However, we can set up other ways to store this. So in this case, we're setting up a Redis connection that basically stores all of the session data inside of this this distributed application that is just storing basically key value pairs. And then if we have a production environment where we have 100 different node applications, they can quickly access that session data from Redis. So this is how you would set up that what's called the session store using Redis. It's just a code example here. So whenever we're setting up the session, the standard configuration data, but down here we would give it the data needed to connect to Redis as a client. Is the value of this clear to people, or is this just like totally abstract and not clear?
I think I would benefit from like a little summary of what it is again.
Okay, so just to go back, so basically it is a tool for caching data between a bunch of different applications, right? And so if we have this environment where we have a bunch of different node instances running in parallel, we have them programmed so that they're stateless, so that each of these instances don't have any data about that persists relative to like the state of their clients. So if we remember before with the example with sessions, sessions are how we keep track of like the state of different client connections and client requests. So we can keep track of, for instance, the number of views, or we could keep track of like their shopping cart, or if they've logged in, we could keep track of like what user is associated with a particular client. That gets saved in the session. However, if we have each of these instances stateless, where they're not saving that data themselves inside of their like memory and some sort of data structure in themselves, we have to have some place else to store that data. One place you could do that would be in a database like Mongo or SQL. However, those databases tend to be a little bit tends to be more overhead in terms of their performance of like looking those things up. They can be fairly optimized. However, for just very quick caching of like key value pairs, Redis is an application that we can use to do that. Let me see if I can just bring up an example real quick of what that looks like. So can y'all see this like example that I have here? I'm sharing this desktop, right? It should say something that says try Redis at the top.
Yeah.
You can see some, okay. So, so let's see if I just do tutorial. So basically all that Redis is it has these very like simple operations like setting key value pairs. So if I so in this case, I'm just setting like server :name Fido. I can just get it back. Reference Fido. I can check whether or not it exists. And this is like this text that I'm typing out are like is basically the command set that's available with Redis. So it's actually a very simple tool. there are other operations like we can set like counters, or we can delete things. And this is kind of getting a little bit into the weeds of how this operates. But basically it's just like this application that is primarily just like a big hash map, where we have key value pairs. So I can set and get keys and values. And so it implements that in a very high performance way, so that we, just to give you an example, like if we wanted to, implement sessions, so sessions, if you remember, we have a cookie, which is just a unique identifier for a particular client session that gets sent along by the client to the server. So what we would probably do is we would set in Redis, we would use that cookie ID as the key, and then we would just have like a big text blob or some kind of blob of data that would be the representation of that session. And so the different instances that we have set up here could then quickly just access that key value pair that's in Redis, and then make modifications to it if something in the session changes. So it's actually a very simple piece of software that is just there to basically serve as glue for like caching data between multiple parallel instances like this. And you could, it's implemented in such a way that you could have many of these instances like connecting to it and pulling out data. Again, I'm not going to have you implement this in class unless you're like looking to, with your final projects, unless you're looking to like support thousands of people. I'm just trying to explain like how this potential architecture would work if you were just trying to like understand how you can build out and scale these applications. So hopefully that explains it a little bit. An additional functionality that Redis provides is a way to basically send messages back and forth from clients using like what's called a publisher subscription model. So this is very similar to like what we're talking about like with Socket.io. So we could set up like a particular like room in Redis where we are, say we're we have like a channel called like room 1, and anytime we send a message to that room, we would, anyone that was subscribed to that room would receive that message. So in a distributed architecture like this, this is potentially useful. So if we were thinking about Socket.io, like we've been talking about for this assignment, the way that is implemented is only within one node instance. That's the only thing that we've looked at so far. And so if you wanted, if you had a potentially like thousands of different clients that were connected to different Node.js instances through a load balancer, we need to think about how we could actually send real-time messages between those different clients. And so using this message passing, the publishing subscription model through Redis, we can basically, we can glue all of those instances together, and we can send messages, or we can instigate messages being sent or received on any of those node instances and sort of have them interconnect. So to do that, there's just a very simple adapter that's implemented for Socket.io if you wanted to use that. So in this case, this is just a package that we download from npm. We specify the host location and port. This is just the defaults for Redis. And then we could have multiple, and then, if we're sending data to particular rooms or things like that, Redis would manage the connecting all of these different parallel instances for sending data back and forth. If you weren't doing that, you would have to look at more like low-level inter-process communication mechanisms. This is basically a way for just like architecting this out in this like scaled up instance. So if you want to learn more about particularly how to do this with Redis and Socket.io, there's a link here. You can write your own. So I was kind of showing some of the code, some of the simple things you can do with Redis in that example. And you can write your own Redis clients to like implement your own functionality if you want to do something that's maybe a little bit more intricate that's connecting all of these different instances. But there are also a lot of libraries that do things like this that you can use so that you don't have to implement things yourself. Which I would highly suggest you do. Hopefully that doesn't confuse people too much. And again, we're not like, I'm not going to require that you implement like an architecture like this. I mostly am trying to sort of like expose you to like thinking about these types of problems. So that if you do like try to do this type of programming like later on, maybe in a job, like you haven't, like these concepts aren't just like completely foreign to you. Other production considerations, we need to be able to handle like server errors and crashes. We need to be able to like modify or update deployed code in a, in a somewhat seamless way, or monitor the performance of like the different parallel applications that we have running to support a distributed service like this. Some tools that you could look at for doing that. Forever is a very simple one, which basically just you set up like, you say like forever, like your node app name, and it basically just runs that continuously as like a process daemon in the background as a service. And if your application throws an exception or crashes for some reason, basically Forever will just restart it up immediately. So that, if you're wanting to keep these things running for a long time and to keep serving people, like you need to be able to basically recover from crashes. And Forever does that for you. It also manages like logs and things like that. So you can log, errors and things like that. PM2 is another tool like Forever that will daemonize node instances. It actually has some built-in load balancing functionality, although my understanding is that it's a little bit less feature-rich as NGINX, but also has a lot of tools for monitoring like the performance of a bunch of parallel instances. Just wanted to like introduce those as like these are available and you might need them if you're setting up one of these things to run in a production environment at some point. But that's pretty much all I have to cover today. I feel like it was very technical and you might all just forget it, but hopefully that is introducing you at least to some of these ideas so that you're not encountering them for the first time in the future. Are there any questions about these things in general, or that I can answer for you before we end? Okay. Well, I'm going to hang around for a little while. And if people have particular things that they want to talk to me about their projects, I'll hang around and we can talk about that in an informal way. Otherwise, that I believe is the end of today's class. So thank you for being here. Something else I should announce is that there is an assignment that's up for the final project sequence now for the ideas. I believe that's due Friday night at 7 to basically have to record like less than a minute of yourself like introducing a project concept. There will be another part of that assignment over the weekend where you basically have to watch other people's project pitches and provide comments on them. So be ready for that, but get your project ideas out there by Friday.
Hey, Dr. Hamilton,
Yeah.
could me and my group stay after to discuss our project idea?
Yeah, of course.
Okay.
But yeah, this first assignment on Friday is just an individual like idea thing. So still submit
it's
that.
not a group idea; it's just an individual idea.
Yeah. So this first thing is just like is an individual idea. So there's research showing that like whenever you're trying to come up with like creative ideas and like brainstorm, it's better for like people to think individually first and then come together as a group, because like if you just start out with like people throwing out ideas like in a group and not thinking about it individually, then people tend to get like fixated on one thing. And so I wanted people to pitch their own ideas first. So but if you have an idea that you want to talk to me about here after class, I'll stick around for that. So all right, I'm gonna start the recording.